And we'll finish talking about exponential and logarithmic functions. That's what I hope to get through. Right, and then tomorrow we start limits, which is the real calculus part of the course. Okay, so let's talk about circles. Okay, circles should connect. What differentiates one circle from another circle?
Radius.
Radius, absolutely, right? Radius is the distance from the center to the circumference of the circle, and if you have a different radius, then you have certainly different circles. What else differentiates?
Area.
The area, okay. Now, how do I compute the area of a circle?
Pi r squared.
Pi r squared. So it's completely determined by
Radius.
the radius. Okay. So the radius is already giving us the area. What else determines the circle? Okay. Let me ask you, is this circle the exact same circle as this one, assuming that they have the same radius? I see some nods. Is this circle the exact same circle? Well, let me help you out. Let me put a coordinate axis in. Okay, so this is 0. Are these the same circles?
They have the same measurement, different location.
They're different location, right? They're the same size, but these are certainly different circles because one is over here and one is over here. Right? So what reference point can I use for the circle? Right, to tell me where it is? Yeah.
The center point.
The center. Exactly. So the difference between these two circles is the center. Okay, of course, where everything else is different too. But once I know where the center is, and I know what the radius is, I've completely determined the circle. Now, how do I write this as an equation that incorporates those two pieces of information? It's called the center of the circle, HK. Well, there's a nice equation. It says that x minus h squared plus y minus k squared equals the square of the radius. So this HK, this is incorporating the information about the center, and the R is incorporating the information about the radius. And so this completely determines the circle. So we want to know this for a couple reasons. One, when we talk about trigonometry of all places. And two, this is really the first example that you want to have in mind when you talk about tangent lines to curves, because it's somehow the easiest. The tangent line to a circle, let's say I draw this point, and I want to draw the tangent line to it. It's going to turn out that that line is always perpendicular to the radius from the center to the circumference. And what does this mean in the real world? Well, this means that, let's say you're, I don't know, you got your nice bucket of water, right? And you start doing that with it, right? And what's happening, right, with the bucket? It's going on the outside. It's going in a circle, right? Now, what happens if, say, the string you're using to swing this bucket around snaps? What happens to the bucket? It goes flying, right? Does it fly in some random direction?
Flies in the same direction that it's on where it was when the string broke.
Okay, so you're saying it flies in the same direction as where it was when the string broke. So let's say my bucket is traveling around and the string breaks. Where does the bucket go? Well, it's going to go in the same direction as the tangent line is. So at that point, that's the direction it's actually traveling in. It will keep going in that direction. So from a physics point of view, it should be clear that, Of course, there's a lot of things in physics that are working in circles or pretty much near circles. So it'd be pretty important to know as much information as you can about the equation of the circle if you wanted to, say, find a tangent line at a certain point. Especially if you have some slightly different information than, say, the center and the radius. And there are a few problems. For instance, if you look up in the Sean books, they'll tell you you have a tangent line, and you know the equation of it, and you know a point on the circle, and perhaps you know the radius or something to this effect. Can you find the equation of the circle? Right, so look that up in your Sean books, and you'll see some nice examples of that. Okay. I don't like that eraser. All right, so that's the circles. Now, typically, if you were studying analytic geometry, you would progress from here to start looking at parabolas, and ellipses, and hyperbolas. I don't want to do that right now. They're all very nice aspects of analytic geometry, all part of conic sections. Very good. We're not going to need them very soon, and so I'd rather postpone talking about them until we're actually going to need them. Fair enough? Okay. So let's let that be the end of analytic geometry for now. Okay. We come back to maybe some things later. Let's talk about trigonometry. Many of you have taken calculus already, and I'm sure your trig is very good. Some of you are not as comfortable with trig, so this is just an opportunity to at least make sure everybody has the same ideas in their head when we're talking about sine and cosine and so forth. All right, let's just go back to the basics. Okay, I have a right triangle. Right? So it's a triangle with a right angle. I choose another one of the angles. I call it theta, because mathematicians like Greek letters. And I'm going to make the following definitions. Well, I wanted to find the sine of the angle. And to do that, it's going to be some quotient of the side lengths. So let me give names to the sides. Okay, so I'll call the legs A and B and the hypotenuse C. The sine of the angle is defined to be the opposite side to that angle divided by the length of the hypotenuse. So A divided by C. The cosine of the angle is defined to be the adjacent side to your angle theta divided by the length of the hypotenuse. So B divided by C. The tangent of the angle is defined to be the opposite side divided by the adjacent side. A divided by B. And you're probably all familiar with some mnemonic to help remember these things. I'll just write it up there for completeness and explain it if you haven't. So this is kind of the standard way of remembering this thing. SOHCAHTOA. Has anybody not seen this before? You haven't? Okay, so let me just quickly explain it. So SOHCAHTOA stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So typically it's taught there's an Indian princess chief, or the daughter of Chief SOHCAHTOA or something. So how are you supposed to remember these things? Now, with each of these sine functions, we also define a co-function, which is just the reciprocal of this function, which just means I take this and I flip it. So first there's the cosecant function. Then there's the secant function. And the cotangent. And you just get one from the other by flipping upside down. And what you'll notice is, of course, if I start with a non-C letter, I should always end up with a C letter. And if I start with a C, I should end up with a non-C. So that's how you can try to remember. Because a lot of people think, oh yeah, sine and secant go together. But no, it's sine and cosecant. You should always co things. And then two co's makes a non-co. As opposed to a cos-co. Okay, so also, if we look at this picture and look at these quotients, it's very easy to see that, for instance, the tangent is the sine over the cosine. Because A over C divided by B over C is A over B. And similarly, all of these things can be written in terms of sine and cosine. So the sine and cosine will be the functions in which we'll be most interested. Because we can always reduce things to sine and cosine. Okay? Let me give you a different approach to defining sine and cosine. One which in some ways is more useful. Okay, I draw a unit circle. So this has radius 1. And I'm going to draw an angle. For now, let's keep it simple. Okay, so again, I have an angle theta. And this radius is going to hit the circumference of a point. And I'm just going to define the cosine to be the x-coordinate and the sine to be the y-coordinate. It's too high. Does it not tilt down?
No. I can't. It's hard to tilt it up.
Oh my gosh, it's too high. That's terrible. Okay. Okay, so I just defined the cosine of this angle to be the x-coordinate of that point, and the sine of this angle to be the y-coordinate of that point. Now, does this make sense as far as this definition goes? Well, if I drop a little line here, let's see, the cosine should be the adjacent over the hypotenuse. Right? Well, the adjacent is the x-coordinate, and the hypotenuse is 1. That's the radius of the circle. So the cosine is supposed to be over here, adjacent over the hypotenuse, but the hypotenuse is 1, so it's just the adjacent. And the adjacent is the x-coordinate, so this makes sense to make the cosine the x-coordinate. Similarly, the sine is the y-coordinate. Well, the y-coordinate is this distance divided by 1. Okay, so it makes sense. It's the same thing. Okay. Now, why is this a useful interpretation? Well, first, what's the equation of this circle?
That one.
There's the equation of a general circle. Thank you, Jesse.
X squared plus y squared equals 1.
All right, what's the center of this circle? This is at 0, right? So it's 0, 0. So this h and k, they don't matter, right? You just get x squared plus y squared plus equals the radius squared, and the radius is 1, so it's just 1. So this is x squared plus y squared equals 1. Okay, so this says that every point on this curve satisfies this relation. Okay? What does that say? Well, here's a point on the curve, and so it must satisfy this relation. Which is, of course, a well-known formula about sine and cosine, right? That sine squared plus cosine squared is 1. It's an immediate consequence of viewing things on here and knowing the equation of a circle. In case you ever want to know how to actually prove that. It just comes right from the circle. Why else is this important? Well, if you talk about right triangles, what can this angle theta be? Well, it should be an angle greater than 0, and it has to be less than 90 degrees, because you can't have two 90-degree angles in a triangle. So you're really restricted to between 0 and 90 degrees. If you use this definition, you can make your angle anything you want. I can put it and make this my angle. That'll be delta. Okay? And it makes just as much sense to define the x-coordinate and the y-coordinate here, and I can define what my cosine and my sine are. here, I get cosine of delta, sine of delta. Okay. And that's the cosine of this angle, and that's the sine of this angle.
Wouldn't it be
Now-
negative cosine?
What's that?
Isn't it negative cosine?
Well, it's cosine, but what you're getting at is the following. What is the value of the x-coordinate here? Well, I don't know what it is specifically, but it's a negative value, right? So this is a case where the cosine is going to give you a negative number, because the x-coordinate is negative. So we can see that if you're over in this side of the graph, any of these points, the cosine is going to be positive. And on this side of the graph, the cosine will always be negative. And if you're looking at the y-coordinates, right, then these are always the positive, so sine will be positive. And down here, the signs will be negative. Not only that, but you can start going around this picture. And when you get back to the beginning, you can just keep going. Right? And of course, if I went around once, okay, well that's 2 pi radians. So 0 is also 2 pi radians. Okay? This angle here is going to be, it's going to look the same from the sine and cosine point of view as if I added 2 pi to it. So the sine and the cosine, they don't care if you add 2 pi. So if you start with like sine of 5 pi, you say, okay, well, subtract 2 pi, I get sine of 3 pi. It's the same thing. Now subtract 2 more pi, I get sine of pi. It's the same thing. So you only have to know what happens the first time around, and then you get it for everything else. Not only that, you can go backwards. Right? If I start from here, I can go down to minus 2 pi. I can go all the way around, go to minus 2 pi, minus 4 pi, and so forth. Right? But it's easy to see what these functions are going to do because it's all defined in the first 2 pi. That's why they're called periodic functions. Right? There's a certain period which they take on all their values and then they start over. Okay. And while we don't need to put the tangent on this graph or any of the other ones because we know we can reduce everything down to sine and cosine. And so it's, you know, we don't gain a whole lot if we try to add these other things to the graph. So this is a very useful way of encapsulating a lot of the information about cosine and sine so that you don't have to remember a whole lot of values. You just draw this picture and say, okay, for instance, if I'm at pi radians, what's the cosine? Well, okay, I just look at the x-coordinate of this point. It's clearly, well, this point is minus 1, 0. The x-coordinate is minus 1. So the cosine of pi is minus 1. And the sine of pi is 0. Okay. Easy enough. Incidentally, an interesting final project would be to explore the connection between this picture, cosine, sine, and the exponential function. Because it turns out that they're all related. You need to do a little bit with complex numbers if you want to do that project, but I think it would be a heck of a project with a lot of interesting things. And you get to talk about one of the most amazing formulas in all of mathematics, Euler's formula, which I'll just quickly write it for those of you who've never seen it. This is really quite a breathtaking formula because it uses e, I, pi, 1, and 0, probably the 5 most important constants in all of mathematics, and they're all related in this very simple way. And you can see the connection if you just look at these sort of circles. So it would be a really nice final project. If you want to ask me about it later, that'd be great. Okay, any questions about trigonometry at this point? All good? Or anything that I put up here? Happy? Yeah? Okay. Very good, very good. One last thing that I want to mention is, in reference to something we talked about yesterday, we saw that if you graph the sine function, well, okay, remember it was a nice curve. Well, remember, it was not an onto function, for sure, right? Because it only went between 1 and minus 1. Was it a one-to-one function? No, because you draw those horizontal lines, right? It hits it infinitely many times. Okay. But if we restricted the the range to just be -1 to 1, and we restricted the domain so that you didn't get any repetitions, you would get a 1-to-1 function. But of course, it's not defined for so long. So I think what do we want to do? Maybe down to here. Down to here. So maybe we choose this domain. Okay, so this is pi over 2. If we look up here, that's when the y-coordinate goes to 1. And this is minus pi over 2. Right? That's if you went down backwards. That's when the y-coordinate would go to minus 1. So this is sine of x on the domain minus pi over 2, pi over 2. And on this domain, it is a 1-to-1 and on-to function. Right? Assuming you're as a function from there to the interval -1 to 1. Certainly not a on-to function on the whole real numbers. But you do have a bijection from this set to this set. And that means you have an inverse function, right? A function which just takes it over here and just goes backwards along this map, right? Anything from over here came from something. That's why it's an on-to function. So just take the number from which it came. Since it's 1-to-1, that's a uniquely defined number. So the inverse function is called arc sine, or sometimes they write it sine to the -1. Well, I usually use this notation, but this is very misleading notation. What the important part about it, though, is you have to be very careful that you know, whenever you're talking about the inverse function, you know what domain, especially when it comes to sine, that you're talking about. So this is a standard domain to use. And there are similar things with cosine and tangent and all the other trigonometric functions. I encourage you to look those up to make sure you remember them. I'm sure you've seen these before. Okay, so let's talk about exponential functions a little bit. Okay, so we're going to start with a real number, A. So recall this meant A is an element of the set of real numbers. And I'm going to insist that I actually have a positive real number. So I denote that with this lower script here, greater than 0. Then A to the x is an exponential function. People in this world talk about something growing exponentially. This is the sort of function they're talking about. At least it's what they mean to be talking about. Some of them don't know what they're talking about. Say it when they shouldn't. This is what they should be talking about. Okay. What can I say about this function? Well, first, the graph of it is very standard. Okay, in fact, we saw this yesterday. So at 0, you get the value 1. And at 1, you get the value A. Now, that A could be above or below 1. I'll graph it up here, but it doesn't have to be. It could be below 1. And then it grows very quickly. Now, as it gets smaller, as the x value gets smaller, this thing does get smaller, but it never quite hits 0. It just keeps getting smaller and smaller, but it never quite. So we have a few properties we can say. First, This is always greater than 0. And let me add a little qualifier there. And now, I'm using a symbol which you maybe have never seen before. So this is an upside down A. Mathematicians get very bored with writing the same things over and over, and we're lazy, so we come up with shorthand. So this is read for all. Okay. So all this is saying is that for all x, right, x of course should end up being a real number, a to the x is greater than 0. What else do we know about an exponential function? Well, what happens if you raise it to a power which is a sum? You've probably seen before that this breaks up quite nicely. It's a to the x times a to the y. And this is for all x, y. Okay. What if I have a subtraction instead of an addition? Well, strictly speaking, that's already handled by this, but let's write it explicitly. This becomes a to the x divided by a to the y. Okay. Now, can I get a problem here? I have a fraction. When do fractions have problems? Denominator is cannot be 0. So can I have a problem with this? Can I have the denominator equal to 0? No, why not? Yeah. It's the first property up here, right? Whatever I put for y, I can't get 0 because this is always bigger than 0. So I'm never going to have a domain problem here. Okay, I don't have to worry that I choose some funky x and y and I end up with a 0 in the denominator. Okay, so I'm always okay. And that's good because you can see this thing is defined everywhere. You don't have to worry. Okay, one more formula. Let's say I take a, I raise it to the x, and then I exponentiate again to another power, y. Remember what this is equal to? That's right. Very good. Okay. It's the same thing as if you multiply x and y first, and then take a and raise it to that power. So these are very nice properties to make the exponential function very easy to work with. Okay. Now let's compare it with logarithms. So as we did with the sine, let's go back and recall something about our graph. Again, was e to the x, or a to the x in general, was this an onto function? Onto the real numbers. Does every real number on this get hit? No, right? Nothing below 0, and not including 0 either. Nothing, no non-negative, no non-positive number gets hit. So it's certainly not an onto function, the whole real number. But if we restrict the range to just numbers greater than 0, is it an onto function? Absolutely. Is it a one-to-one function? Yes. So that's one more property maybe I can put down here. Because it's a one-to-one, that says if I take two numbers and I take a and raise it to those two numbers and I get the same thing, I must have been starting with the same thing. I can't take two different numbers, raise a to those numbers, and get the same thing. Because it's a one-to-one function. The only thing which goes to this point is 1. Nothing else like that. So if I view the exponential function as a map from all real numbers to the positive real numbers, I have a one-to-one onto function. It's a bijection, which means there's an inverse function, right? The function just takes a positive real number and spits out the number which went to it. We call that the logarithm. So if a is greater than 0, then we're writing log base a of x is the inverse function of a to the x. So the way you always want to think about the inverse function is, I mean, you imagine you guys are old enough to remember VHS video cassettes, right? Okay, good. You didn't all grow up with DVDs all the time. Okay, so remember what happened when you get to the end of the tape? What do you have to do? You have to rewind it. Okay, now if I start at one point and I run the tape to the end, and then I rewind it, where am I? Exactly. I'm right back at the same spot where I started. Okay? That's what inverse functions are supposed to do. I start here, I use one function. The inverse function just sends me right back to where I started. It's just rewinding the tape. Okay? Now let's say I start at the end of the tape, and I rewind, and now I watch. Where am I? Again, you're at the end. You're back where you started. Right? So it doesn't matter with an inverse function whether you go this way and then back, or this way and then back. You always end up where you started. And that's how you want to think of inverse functions. So let's see how that applies in this case. If I take, say, the logarithm, base a, of a to the x, what should I get? Well, this is a composition of two different functions, a function and its inverse function. I play the tape, I start with x, I play the tape, and then I rewind the tape. So where should I end up? At x, back where I started. What if I do it backwards? Okay, I start at the end of the tape, I rewind, then I play the tape forward. Back where I started, right? So what should this be? Is it, well, let's see, I start with x. Okay, I'm starting with x, so that's always my input, right? It's always x. Rewind the tape, watch the tape. Gotta be back at x, right? That's what inverse functions are going to give you. Another example of inverse functions working in that same way. Let's take the function x cubed. Right? Now in your head, you should automatically be graphing that sucker. Because we saw that yesterday, right? Okay. It's that cool thing. There's your x cubed. Okay. 1-to-1 onto function, right? Cool. Then you don't even have to restrict the domain, you have to restrict the range. It's beautiful. Works great. Okay. What's the inverse function? Well, the inverse function is a function that is going to do everything in reverse. So if I take a number and I cube it, how do I get back where I started? Exactly, the cube root. So that must be the inverse function. So I'll write this as x to the 1. Okay, or the cube root of x. Okay, so what is the cube root of x cubed? It's x, right? You all know that. Okay, but let's see what you're doing from an inverse function point of view. I start with x. I run the tape forward, I run the tape backwards. I end up with x. Let's do it the other way. I start with cube root of x, and I cube it. Well, run the tape backwards, run the tape forwards. I must be backwards first. That's the idea behind inverse functions. It doesn't matter which order you do it. You always end up back where you started. So just a quick, fun example of this. So let's do the arc sine of x, and then we're going to do e to the arc sine of x. Now we're going to do tangent of that, and we're going to do tangent, and arctangent to that, tangent of that, and then natural log of that.
When you say we,
I mean you. Okay, this looks really horrible, right? But let's see what's going on. Let's look for patterns. Here I have a tangent and an arctangent. Right, that's the inverse function. Okay, and let's assume I do everything so that I have no domain problems, because there is a domain problem in here. Don't worry about that for now. Although actually here I'll switch it around, and then there should be no domain problem. Okay. What should arctangent and tangent do in this? They just cancel out, right? Because I have something, and some input. I run the tape, I run it back. I should be back at the same input. So I can simplify this to natural log of e to the arc sine of x. Well, now look, e, remember, this is the base of the natural logarithm, right? So in case you don't know this, log base e of x. We write that as ln of x. Okay, read as the natural log. So these are, ln of x is the inverse function to e to the x. So what are ln and e going to do? They cancel out, right? Run the tape forward, run the tape backwards. Okay, so this looks really nasty, but it's really just the same as arc. There's a lot of fun mathematics you can do by playing this sort of thing, where you take, for instance, 1 + 1 = 2 and start rewriting 1 as different expressions, and then start tacking in some unnecessary inverse functions, and maybe throw in some derivatives and integrals to make everything look even nastier. And then you show this long equation on the board, and you say, I've proven this. And step 1 + 1 = 2. So, fun stuff you can do. Okay, now let's just finish up with these logs because we're almost out of time. We have all these properties of exponentiation. And then we know that this log function is the inverse function of exponentiation. And whenever that's the case, there's a way of translating these properties about exponentiation into properties about logarithms. So let's just briefly recall how they translate. So for instance, if you have the log of a product, this ends up being the sum of the logs. That is a direct translation of this property of exponentiation. You see how the product here turns into a sum? The same thing is going to happen if you have a quotient. If you have an x over a y, it's going to turn into a difference. What about this property? This property is going to say that if you have an exponent, the right way to interpret this is that you can bring this exponent in front of the log. Okay? And then what about this last property? Well, remember, this last property was really just saying you had a one-to-one function. Now, is the logarithm a one-to-one function? Okay, let's see, let's graph it. Recall from yesterday, the graph, the logarithm looked like this. Is that a one-to-one function? Absolutely. You get no repeats. Cool. So we should be able to write down the same thing. We do. If log of x equals log of y, this is the same as saying that x was equal to y. Okay. Now, there was a way to see that this function was one-to-one without doing anything. Absolutely, absolutely. If you start with a one-to-one function and you restrict the range so that it becomes onto, you can take the inverse function. That inverse function has to be one-to-one also. That's not hard to see if you think about it. So as soon as you start with a function and you look at its inverse, you know you're going to, if one of them's, you have one of them one-to-one, the other one has to be one-to-one. Otherwise you're going to have an inverse in the first place. And whenever you have some function and you know properties about it, and you know that it has an inverse function, you should immediately try to prove properties about the inverse function that mimic the ones for the original function. So things you know about sine and cosine, it's at least worth looking at. Can I say something similar about inverse sine, right, or arc sine, and arc cosine? It's a little harder with those, but with exponentials and logarithms, you can say some things. Okay, so tomorrow we start with limits. So that's when the calculus really begins. There's also going to be a quiz tomorrow, and it'll be on stuff from the last 2 days. So recall the way I'm going to do the quizzes. You're going to work the quizzes first by yourself, and then I'm going to give you the exact same quiz, but I'm going to put you in groups. And your grade will be half based on your individual, half based on your group. Okay? Any questions?